Okay, welcome to the applications of the definite integral unit and AP Calculus. As you can see, the first really quick topic is for BC. If you wanted to find the length of a curve from A to B, you just have to use the equation integral from A to B of the square root of 1 plus the derivative squared, where A and B are the x values of the endpoints. Okay, like I said, really quick. Now the next topic. If we want to find the area in between two curves, the first step is identifying which curve is on top and which one is on bottom. So this is the blue one's on top and the red one's on the bottom. And then find the x values of the intersection points. In this case, it is 0 and 1. Then we're going to use the formula, the integral from A to B of f of x minus g of x, where f of x is the top curve and g of x is the bottom curve. Sometimes one curve is on top at first, then the other curve goes on top. In this case, if the three intersection points are A, B, and C, then we're going to use the formula, the integral from A to B of f of x minus g of x plus the integral from B to C of g of x minus f of x dx, where f of x is the top curve at the start and then g of x is the bottom curve at the start. Basically, we split it up into two different problems. Other times, you don't really have a top curve and a bottom curve. Instead, you have a left curve and a right curve. In that case, we'll do everything in terms of y. If this isn't that intuitive, try tilting your head to the right so that now there is a top curve and a bottom curve. Anyways, so first you'd have to rewrite the equations to solve it for x, so that if x is equal to something, and then use the equation, the integral from A to B of f of y minus g of y dy. In this case, A and B are the y values of the intersection points, so you'd have -2 and 1. F of y is the right curve, and g of y is the left curve. Now we'll move on to what is probably the most challenging topic in AB. Basically, what we're going to do here is take a curve, rotate it around a line, and then find the volume of the shape we created. In this graph, the 3D shape will look kind of like a cup. So to find the volume, first we need to find the radius r, which is the distance between the curve and the axis of rotation. I'd recommend using a capital R, because as we'll see in a few minutes, there can sometimes be two radii, and it's really important to keep them straight. After that, identify the x values of the endpoints A and B. Now, just use the equation pi times the integral from A to B of r squared dx. Don't forget the pi. The volume is always going to be positive. If it's negative, you did something wrong. So the most challenging part of these problems is identifying the correct radius. So let's practice that. In this first example, the distance between the x-axis and the graph is just sine of x. So that's going to be the radius, sine of x. On the right graph, we're rotating around y equals 4. So this distance is what we want. Since this distance is extra, this x squared part is extra, the radius will be the total distance 4 minus the unnecessary distance x squared to give the radius of 4 minus x squared. For the bottom graph, notice we're now rotating around the y-axis. If we were solving this, we'd have to rewrite the equations to solve for x, use the y endpoints, and so on. But for the radius, it's going to be this distance. Since f of x is the square root of x, solving it for x gives x equals y squared. The radius is how far out it goes in the x direction, so the radius is just y squared. Another type of problem you might see is when you're rotating around a line that isn't even touching the area that you're rotating around. So when we rotated, it's going to be this like area of empty space in the middle. This is when we have two radii. The first one, I'll call it little r, is the distance from the axis of rotation to the start of the curve. In this case, it's going to be this distance, or just 3. The other radius is from the axis of rotation to the upper part of the curve. In this case, that would be 3 plus whatever the yellow part is. The equation for this is pi times the integral from a to b of r squared big R squared minus little r squared. Make sure to notice that each radius is being squared separately. Let's try some more radius practice. On the left curve, we're rotating around y equals -3 down here. So little r is the distance from that line to the black curve, which is 3 plus x squared. Big R is the distance between the dotted line and the red curve, so all the way up there, which is 3 plus the square root of x. On the right picture, now we're rotating around a vertical line, so everything needs to be solved for x. And just to be clear, this is the area that we're rotating. So since g of x is equal to x squared, solving that for x gives x is equal to the square root of y. The other equation here is already solved for x. So little r now is the distance from the dotted line to the red area, which is 2 plus y squared. And then the big R is from the dotted line all the way to the black line, so 2 plus square root of y. Finally, let's talk about volume with known cross-sections. This is when we have a certain area, and there are an infinite number of shapes on that area. In this case, we have a bunch of semicircles, so we need to find a volume. This shape sort of looks like if you took an ice cream cone, chopped it in half down the middle, and then laid one of the halves down. So the area of a semicircle is 1/2 pi r squared. Be really careful with the r's here. In this case, r is the radius of the semicircle, which is this distance, for example, and not the entire thing like we've been using so far. So the radius is half of the y value, so half of -1/4 x plus 1, so half of that. Right there, so that's the radius. And then now I can plug this into the formula for the area to get 1/2 pi and then all of this. So this is the area of just one semicircle for one x value. So we need to find all the semicircles. Therefore, what we're going to do is we're going to integrate this from 0 to 4, since those are the endpoints. That gives the integral from 0 to 4 of blah 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 dx. Just like highlight there. Should go around that. Okay, basically what we did is we took the area of one shape, then we integrated it to find the total area. And that was it. I hope you found this quick review helpful, and I'll see you next time.